On October 3rd, 2025, a fleeting window opened above Mars. The ExoMars orbiter captured the first clear images of the interstellar comet 3I Atlas from a vantage point impossible to achieve on Earth. Within hours, scientists worldwide raced to download this raw Mars data, as early analysis suggests these images could rewrite our understanding of the object's true path, structure, and even its origins. Some researchers theorize that this unique geometry could finally reveal critical details that Earth-based telescopes will always miss. What did Mars see that humanity never could? And why has the global scientific community dropped everything to decode these signals? The stakes of this cosmic moment are higher than anyone expected. October 3rd, 2025, Mars and 3I. Atlas are locked in a rare cosmic alignment, the kind that planetary scientists might see once in a career. For a few tense hours, the ExoMars orbiter sits in precisely the right spot, tens of millions of kilometers from Earth, but almost on top of the interstellar comet's path. Earth's telescopes are blinded by the sun at this angle. The glare washes out any chance of a clear view. From Mars, though, the sky is dark and the geometry is perfect. Every second counts. The comet won't come this close again, not in our lifetimes, and the window for imaging is measured in minutes. Miss it, and the next opportunity could be decades away or never. The urgency isn't just about getting a better picture. It's about what only this angle can reveal. The distance between Earth and Mars, about 97 million kilometers that day, turns the two planets into a giant pair of eyes. That baseline is the key to true three-dimensional sight. With data from both worlds, researchers can finally pin down the comet's real position, speed, and trajectory, not just a projection on the sky. That's the kind of measurement that decides whether 3I Atlas is a chunk of rock, a ball of ice, or something stranger, maybe even a fragment from a planetary system we've never seen before. Mars' perspective also flips the lighting. The Sun, the comet, and the orbiter form a wide triangle, so the comet's coma and tail are illuminated from a direction Earth can't match. Shadows fall differently, and subtle features, jets, fans, or color changes might stand out only in this configuration. Some teams have already started speculating that these images could show outgassing or surface patches invisible from any other angle. This is why the pressure is so high. ESA's mission planners have just one shot to retarget the orbiter's camera, track a target that's 10,000 times fainter than usual, and hope the data makes it back to Earth intact. The entire sequence is a gamble. But the potential payoff, a leap in understanding interstellar objects, means scientists around the globe are glued to their feeds, waiting for the first signal that the gamble paid off. ESA was never meant for this kind of target. Designed to map the Martian surface in color and stereo, its normal job is to scan broad, bright landscapes, canyons, dunes, ice caps, each one reflecting sunlight thousands of times stronger than the faint speck of 3I Atlas. On October 3rd, the mission team had to gamble. The comet, at its closest, was still 30 million kilometers from Mars, and by all accounts at least 10,000, sometimes 100,000 times dimmer than what ESA usually sees. Nick Thomas, the principal investigator for ESA, put it plainly: the comet is around 10,000 to 100,000 times fainter than our usual target. Tracking something this faint isn't just a matter of pointing and clicking. The orbiter's commands had to be rewritten on the fly. Exposure times were stretched to the limit, and the camera's settings pushed far past their comfort zone. Engineers had to account for the comet's rapid motion against the Martian sky, which risked blurring any signal into background noise. Even a whisper of error, timing, focus, tracking, would leave only blank frames, no different from the cosmic static that fills the space between planets. The decision to retarget ESA didn't come lightly. Every second spent on 3I Atlas meant less time for the orbiter's regular science program, but the opportunity was too rare to pass up. The team ran simulations, checked photon counts, and weighed the risks. In the end, they fired off a burst sequence, hundreds of images, each one a long shot, hoping a few would catch the comet's faint glow. What makes this feat remarkable isn't just the technical challenge, but the willingness to risk precious mission time on a target so uncertain. ESA was built to scan Mars, not chase interstellar visitors. Yet, in these hours, it became the first camera from another planet to lock onto an object from beyond the solar system. The images that came back are fragile, each pixel a product of careful timing and real-time adaptation. Later, when researchers begin to process and combine these delicate frames, the true scientific payoff will depend on just how well the team threaded that needle. For now, though, the world has a new kind of picture, the first clear look at an interstellar comet captured not from Earth but from orbit around Mars. Parallax is a simple word for a powerful idea. When two observers are separated by a great distance, each sees the same object from a slightly different angle. For 3I Atlas, the physical gap between Earth and Mars, almost 97 million kilometers on October 3rd, turns the two planets into a cosmic pair of eyes. This setup isn't just a neat trick, it unlocks the third dimension. By comparing images from both worlds, researchers can triangulate the comet's true position in space, not just its apparent path across the sky. That means a direct measurement of distance, velocity, and the subtle shifts that betray its real trajectory. It's the astronomical equivalent of depth perception, and for an interstellar visitor, it's the only way to pin down where it's actually going. But the geometry goes deeper than just distance. The phase angle, the angle between the sun, the comet, and the observer, shapes what's visible in each image. From Mars, the sun lights up 3I Atlas from the side, casting shadows and highlighting surface features that would be hidden in Earth-based views. This sideways illumination is like shining a flashlight across a dusty window. Every bump, every jet of gas, every patch of roughness can stand out in sharp relief. Some teams are already running simulations to predict how these lighting differences might reveal details about the comet's surface or even its internal structure. Others are focused on the coma, the cloud of gas and dust that surrounds the nucleus, looking for changes in brightness or shape that only appear at certain angles. There's another advantage to Mars's orbit, the out-of-plane perspective. Earth and Mars don't just sit on opposite sides of the sun. Their orbits are tilted relative to each other, meaning Mars can see above or below the plane of the solar system, giving a look at the comet's north or south pole, views that are impossible from Earth alone. For a tumbling object like 3I Atlas, this out-of-plane angle is essential. It lets scientists watch for rotation, track how sunlight glints off different faces, and spot any asymmetries in the coma or tail. Some researchers theorize that this is the only way to catch certain features like jets or fragments that might be hidden in a flat head-on view. All these geometric tricks come at a cost. The raw images are just the beginning. To turn them into real measurements, teams have to account for the exact positions of Mars, Earth, and the comet down to the second. They need to correct for light travel time, adjust for the phase angle, and stack dozens or hundreds of exposures to tease out the faintest details. The baseline, the vast distance between the two planets, makes the math harder, but the payoff is a leap in precision. What looks like a faint speck in a single frame becomes a data-rich target when viewed from multiple angles. This is why the geometry matters so much. It's not just about getting a sharper picture, it's about seeing the comet as it really is in 3 dimensions under changing light from above and below. That's the promise of Mars-based imaging, and it's why every pixel in these new datasets is being scrutinized by teams around the world. The hope is that somewhere in the interplay of angles and shadows, the true story of 3I Atlas will come into focus. Getting data from Mars to Earth is never simple. The ExoMars orbiter sits nearly 20 light-minutes away, and every bit of information has to crawl through a narrow pipeline shared with all the usual Martian science, engineering status, and routine housekeeping. For the 3I Atlas campaign, that meant the Mission Operations Center had to make tough calls about what got priority. High-value images of the comet, packed in their original FITS format, were slotted for immediate downlink. At the same time, engineers scheduled redundant transmissions knowing that a single corrupted packet could erase hours of irreplaceable science. ESA's standard is caution. Critical datasets are sent multiple times on different passes to guard against solar storms or antenna dropouts. With 3I Atlas, the stakes were even higher. The raw images unprocessed straight from the detector went first, followed by calibration files and engineering logs. There was no embargo, no proprietary lockout. As soon as the packets hit the ground, they went straight into the public archive. This open-door approach isn't the norm for every mission, but for a one-time interstellar visitor, the logic was clear. The faster the data reached the world, the faster the science could begin.